So okay, so what you need to do, you need 4 switches across one flying cap, and depending upon where you connect V in and V out, that so you short if these 1 and 2, so there are 4 terminals 1 2 3 4. So if you short 1 and 2 and apply V in here, and on the other 2 switches, one is connected to ground in one phase and other is connected to V out in the other phase, then so what you are doing actually, you can see what is happening during this phase 1. So this is your phase 1 red. So during phase 1, what is the charge across this capacitor? V in. Okay, V in into C fly. So V in into let us call it C fly. Equal to, what is the charge across this capacitor during phi 2? V out minus V in. Okay, you have to look at the polarity. You cannot flip the polarity, otherwise you will get negative voltage. That is the voltage, and what is the capacitor will remain same. So this gets cancelled out. So what you get? V out 2 times V. Okay. Now let us look at the buck. This is half V in by 2. So now it is exactly the flipped version of this. Now V in becomes V out, correct, and V out becomes V in and ground remains same, correct. If you remember the how we converted a buck into boost, we just flipped the input output. So it's similar situation here. So let's see. So what is happening in phi 1? What is the voltage across this capacitor phi 1? During phi 2, and this is phi 1. Okay. So during phi 1, what is the charge? V out minus V out minus V in into C fly equal to, look at the other phase, not V out, minus V out. Because in phi 1 your charge is this direction, and your phi 2 the other plate is actually connected to V out. So that is why it is a minus. So again this gets cancelled out, and your V out is V in by 2. Okay. Let us see the inverting case. So during phi 1, what is the charge? Let us say this left hand side is plus, then V in equal to, now during the other phase, what is this? Minus V out. Okay. So now if I want to do, let us say, divide by 3, how can I do that? So if I want any other ratios, I know the charge remains same. If the capacitor remains same, they are cancelled out. But nobody is forcing you to have the same cap during phi and phi bar. You can have a different caps. Okay. So let us see how we do. V out equal to VDD by 3. if you look at the voltage across this capacitor, that will be equally divided. Okay, so this will be VDD minus V out by 2, and this will be so Q is how much? VDD minus V out by 2 multiplied by C fly. So Q total is twice of, because we have two capacitors here, okay, and when you connect in parallel, the total charge will be added. So you can think of like you have two buckets, okay, and when you pour both the buckets in another cap, so you will get a 2x charge. So each cap charge of each across each cap will get added when you dump on the output capacitor. Sorry. Okay. Now during this phase, let me move this. We have a twice cap now, 2 into C fly multiplied by V out. So which means Q total during phi equal to Q total during phi bar equal to twice of V out, which implies V out equal to VDD by 3. Okay. So you can do VDD by 4, VDD 5 by 5 by connecting more capacitors, but it will require more switches. So if you I want to exactly implement this, then let's see how will it be. VDD C fly, let's say this is phi, phi bar sorry phi bar. Okay, so during phi this switch will be on. Okay, so this is on, and this is on. So what is, these two capacitor will come in. So let me draw like this. This is the actual path. Okay. So the voltage across these two capacitors will be VDD minus V out, and they will be in series. Now let's see during phi bar. So during phi bar, we need one more switch here. So, this will get connected to the output 5 bar and this will be grounded. So, one capacitor between V out and ground, and this will get connected to V out and this will be grounded. So, both will come in parallel. Okay. So, you will get this configuration. So, this is your one and the second one is this. Okay. So, if I want to do, let us say VDD by 4, you can do in the same manner, or another option would be, you already know how to do VDD by 2, you can cascade the same and you will get VDD by 4. So, whichever gives you lesser number of switches and lesser number of capacitor, you can opt for that. So, and you already know VDD by 2 requires only one capacitor. So, if you cascade them, total number of capacitor will be 2, and if you do VDD by 4 here, you need one more cap. So, so obviously the number of capacitor looks lesser, and hopefully the number of switches will also be less, because 3 capacitor will require more switches compared to two capacitors. So, this same structure, 2 capacitor and those switches are connecting them in series and parallel. So, I have 5 volt input. So, your output should be 1/3 of that. So, 1.67. So, it's 1/3. Okay. This divide by 2. So, you get 2.5 volt. Usually this is how you do. You have to basically make a parallel and series combination in 5 and 5 bar and get a different ratio, so that you can get different output voltages. So, as we looked into this regulated charge pump, if you remember, and if you do not regulate at its gain, so let us say I have done a 2x charge pump, but my output to input ratio is not 2x, but let us say 1.5x or something, then your efficiency will drop, okay, because you are not allowing your charge pump to settle. So, if I want to cater to wide range of voltages, V out over V in, then you need multiple ratios. Okay. If you do not have multiple ratios, what will happen? So, this is your LDO actually. So, let us say my V out is here, I think V out is 1.2 volt or so, and V in is 2.5 volt, correct. So, for half 1 by 2, 1.25 volt. So, if your output is varying, so here you need roughly 1 by 3rd. So, 2.5 by 3 is roughly 0.8 volt or so, okay. So, this is the point where your dropout is maximum, which means LDO will have very bad efficiency. But if I have a charge pump which can do 1/3, then you can see efficiency is much better. But now if I move away from this ratio, then you can see efficiency is dropping. So, I would like to operate this charge pump always at its gain, not away from it. If I am, so let us say if I am operating away from it and I do not have this 2:1, if I do not have 2:1, what would happen? It will keep going like this, okay. Efficiency will keep dropping, but when I am moving away, what I did actually, I switched to 2:1. So, now efficiency will improve, and when I have a half, which is roughly 1.25 volt, your efficiency will peak again and start dropping when your output voltage is increasing. So, if I do not have, let us say 1:2, I mean I do not have this other 3:2 ratio, then it will keep dropping efficiency. But I have a 3:2, so I will switch to that, and then again. So, by having more gain settings, I can have basically high efficiency across wide range of output voltages, or you can say output to input ratio. So, it is not necessary that output is changing, output may remain fixed and input is changing. So, it is the same thing actually, it is just a V out by V in ratio. Okay. So, that is the advantage of having multiple gain settings. So, usually what you do, you have multiple switches and you configure the switches based on in which gain settings you want to go. So, just like we looked at one edge bridge architecture, this guy, and this can be configured in two VDD and VDD by 2 and VDD also. VDD is nothing but it's a bypass mode. So, you just short V in and V out. So, we can configure it in 3 settings, forget about the negative voltage, let us say we always want, let us say, positive voltage. So, you can have a 3 settings with this depending upon how you configure the switches. Okay. So, which means more gain settings will require more switches and it may require more capacitors also. Let us say if I want VDD by 4 or VDD by 3, then you may have to connect the capacitors in series and parallel to get finer ratio. Then you may require more capacitors also and more switches. So, as you keep increasing the gain settings and make it very high resolution, your complexity will get increased and you may not be able to achieve the same efficiency, because your switches will have loss, CV square F loss, then your conduction loss will also increase, because in series there will be multiple switches connected. So, everything will contribute to loss and your efficiency will decrease, but overall average efficiency will look better. Your peak efficiency may drop. So, let us say if I had only one settings, so instead of this 70%, it may be looking at 80 or above 80% if you have only one settings. But in the same switch capacitor converter, I have multiple settings. So, you may drop 5-10%, but on an average you can say efficiency will be looking better compared to an LDO or compared to a single setting switching converter, DC, this switch capacitor switching converter. Okay. Okay. So, this is a product actually LM3352 from TI, and it has multiple settings, and you can see this they have a switch array here and all these capacitors are external. So, they are having 3 capacitors here, okay, and V out is the C hold is here. So, all 3 are flying capacitors. Okay. So, they can be connected in parallel and series depending upon this switch configuration, and they are also regulating the output with this. Okay. So, they have a gain setting. So, if you remember, we talked about how you control the gain setting. Okay. So, you can have a comparator and your accumulator or up down counter, and that code will decide basically what gain settings you need to have. Okay. So, now in the buck mode they have this 1 by 2, 2 by 3, 3 by 4. So, 3 almost 4 settings if you include 1 also. And so, 1 is nothing but bypass. So, they have a different region, like in first region they go from maximum gain 2 by 3 to half, in the second region 2 by 3 to half. So, these 2 regions are same. In third region they go from 3 by 4 to 2 by 3. Okay. Fourth region 1 to 2 by 3, and sixth region is nothing but bypass, and then after that they start boosting. So, you can see how many switches are used here with the 3 capacitors 1, 2, 3. So, they have too many switches. So, they can be connected in series and parallel. So, like more than 10 switches here, like 13, 15, 17, yeah, looks like 19, almost 20 switches. So, I mean there is a trade off between like obviously whether you want to maintain the average efficiency or you are looking for the peak efficiency. If you are only interested in one gain setting, then you can do. So, and we already talked about in what case we are interested in only in one gain setting. We talked about cascaded switching regulator and inductive switching and switch capacitor. If you want to convert 10 volt to 1 volt, so you can divide by 2 using switch cap and then do a buck. So, same thing you can do with the LDO also. So, let us say I have this LDO, VDD is 2.5 volt and V out is, let's say, 1.2 volt. So what is the efficiency? Close to 50%. Huh? Yeah, close to 50%. Okay. Now if I do this, so what is this? 1.25 and then LDO. So dropout is only 50 millivolt here. And what is V drop here? 1.3 volt. Huge difference. So let's say this guy is 90% efficiency. Not difficult to achieve with single gain setting. So what is the efficiency of this regulator? 1.2 divided by
1.2,
how much?
96%.
96. So what is total efficiency? 0.9 into how much? So 50% versus 86%, huge difference. Okay. And if you are looking for very low current, let's say order of 1 milliamp or so, then these capacitors can be integrated on chip, then you don't require. But this guy is I think load current is they are maximum catering to 200 milliamp or so, which is impossible with the on chip capacitor. So that's why they are using external. Okay.